Okay, so in the previous video, we learned that we need to change our approach to describe the probability, and our new approach, which is a more general approach, is the CDF, is based on the CDF. Like we are calculating cumulative distribution at a lot of points x, like value x, then we can describe the probability distribution. Okay, so suppose that we are going to use we are going to study the total size coffee amount. How much coffee is in a total size coffee? I made up this example when I see the news about lawsuit against Starbucks. So like someone sued Starbucks because uh, he or she claimed that the Starbucks iced coffee has too much ice, but too little coffee than it's advertised. So I don't know if it's the result of that. After the lawsuit, I feel like there are less ice in iced coffee. It's not as cold as before. There are more coffee, which is good, but there are not enough ice, I feel like. Anyhow, so let X be the amount of a total size coffee. So you randomly choose a total size coffee and then measure its coffee amount. How much is that? And suppose that you know the CDF at 3 points. The CDF at 11.9 means that it's 5%. That means that 5% of coffee has have less than 11.9 ons. Okay, and the second information we have is this, which means 30% of coffees have 12 or less ons, 12 ons or less of coffee. Okay, and 90% of coffee had 12.2 ons or less. So these three CDFs give you the probability less than a certain amount. Excuse me. So then, based on this information, can you calculate this probability? So we only have three CDFs. Can we explain this probability? So the idea is simple. We know that probability smaller than 12 is 30%. Probability smaller than or equal to 12 is 30%. That means the other side, probability greater than 12 must have 70%. So you can explain like this. Probability x, random variable, greater than or equal to a certain value is 100% minus smaller than or equal to that value. I included equality in both inequalities. I mean, like so. So this does not matter because 1 point doesn't matter. The idea is if you choose a point on an interval, on a line, you choose a value x, then you know the CDF tells you probability on the left-hand side, lower side. You know this probability. But you want to know this probability, then simply you can use the fact that adding these two sides probabilities must be 100% always. So probability greater than x is 1 minus f. But equal, like strictly greater than 12 or greater than or equal to 12 are the same because 1 point does not change the different probability. So the answer is 70%. So the CDF is defined as smaller than or equal to, but it also tells you the probability greater than something. So smaller than something, greater than something are basically the same information. So CDF tells you about that. And then how about this? Can you find, based on the same information, At 3 points, can you find the probability between 11.9 ons and 12.2 ons? You can expect like easily based on you are going to use these two information, because the first one is about 11.9 and the last one is about 12.2. So think about this. 12 point less than 12.2 ons is 90%. So if you randomly choose 100 coffees, 90 of them are less than 12.2 ons. But among them, 5 of them are even less than 11.9 ons. So then if you think about this, I am looking for coffee. I'm counting coffees that satisfy two conditions. First, less than 12.2 ons, but greater than 11.9 ons. Okay? So in our previous counting, 90 coffees satisfied this condition, this inequality. Out of 90, 5 fails this inequality. That means 85% of coffees satisfy both. Visually, you can write it this way. Choose 2 points on the interval. Choose 2 points x and y. Then the cumulative probability gives you probability on the left-hand side of a point. So at x, you know this probability. At y, you know this probability. You know the length of the interval on the left-hand side of the point. Okay, so that is the cumulative probability, right? But what you want to know is the length, which is the probability length in between these 2 points, right? How can you calculate that? If you take probability as a length, it is easy. You know the length of the larger interval, and you know the length of the smaller interval, and of course their difference is the length of what we want to know, the interval we want to know, right? So probability of an interval greater than something but smaller than something can be calculated by differencing two CDFs. That's how we calculate probability on an interval with two endpoints, okay? By simply taking the difference. So what I'm saying here is, like, based only on the CDF, CDF is defined as the probability smaller than something. But I illustrated the case that so I illustrated that the CDF also tells you information about the probability greater than something. So originally it's defined as smaller than something, but it also tells you greater than something. And also you can calculate probability in between something, between 2 points. Okay, so if you know the CDF, you can calculate any form of probability. That is what I wanted to tell you here, and so I justified our new approach based on the cumulative distribution function works. Okay, if you can calculate these 3 types of probabilities using inequalities, then you can calculate any probability, right? So, okay, then now we will think about this this example. So then it is easy to see that 5% is less than 11.9, and difference between them, 25% is in between 11.9 and 12, and 60% is in between 12 and 12.2, and 10%, the remaining 10%, is greater than 12.2 ons. Okay, so then, so far, I pretend as if the probability equals the length because it helps you to understand the probability for continuous random variables. But actually, it is not proportional. In this example, my argument was wrong. Like I said, as if the probability is a length, so you can take the difference. This is not correct. This illustration, this diagram, is not exactly correct. It contains the intuition, but mathematically it is not exactly correct because probability is not proportional to the length anymore in our example. See? So in the interval between 11.9 and 12, which is 0.1 length, contains 25%. But in another interval with twice larger interval, a twice larger length contains more than twice of the probability. So it is not proportional. If they were proportional, it should have been 50% or it should have been 30% because the length is exactly double. Length is double, but probability is more than double. Something is not proportional. So length is not sufficient to describe the probability. Our previous example was just an example, just to help you understand. The intuition survives, but not general enough. So let me generalize that intuition. So think about dimensions. So the main problem in continuous random variable is about the dimension. So you know, a line is one dimension. There is only one direction, right? So then we measure a line with the length. Length is a measurable line, okay? And if you reduce the dimension to 0, it is 1 point. Just a line is an infinite collection of infinite number of points. So 1 point does not have any length, does not have any measure. It only has a location, right? So point is 0 dimension, does not have any direction or size, right? So if you collect infinite number of points, then it becomes a line, it has a direction, it has a measure, which is called the length. Now, if you collect infinite number of lines, then it becomes a square, right? Two-dimensional plane, I would say. Plane, so line, if you collect line, infinite numbers, then it becomes two-dimensional plane or a square, and then you measure the size of a square using area. The area is width times height. You know, right? It's an area. And you can keep going like a third dimension. If you add third dimension by collecting infinite number of squares, planes, so like papers are accumulated, then it becomes a cube. Three-dimensional cube is the three-dimensional object, and then its measure is the volume, like width, height, and then depth, right? So so far I explained based on the first 0 and the first dimension, right? I said continuous random variable is defined on a line, first dimension, but one outcome is just 0 dimension. It does not have any size. Size is probability, right? So a point has no probability, but a line can have a probability, which can be thought of as a length. However, length was not general enough to describe a probability. It is not exactly the probability. So we are going to generalize to two-dimensional case. We are going to think about area. So this is general. From now on, probability will be measured as an area. Okay? Think about this. Now we think about two-dimensional graphs. So this x-axis, horizontal axis, is the same axis, like say 11.9, 12, 12.2. So 3 points, and we add another dimension up here. Okay? This doesn't mean right now, but what we want here is we are going to we wanted to calculate probability on an interval, like interval probability between 11.9 and 12. And then how can you calculate that? It is not just length, but you need to take into account the height, right? So the area below the curve, below this line, is the probability. For example, this is how you calculate probability on this interval. On that interval, there is a square, two-dimensional object. So you calculate the size of that object, two-dimensional object, which is like width times height. So probability is 25%. So now it means something. We need to multiply 2.5 to obtain the probability on here, right? Similarly, if you want to calculate probability between 12 and 12.1, the width is still 0.1, but height is slightly higher, 3. So probability is 30%. Okay? So probability is 30%. That means this interval contains more probability than another interval that has the same length. Length is the same, but heights are different. So by adding another dimension, height dimension, you can make the probability more flexible. Excuse me. So, as you can see, if you have this kind of curve, you can calculate probability as much as you want. Whatever probability can be calculated, right? So, for example, if you want to calculate probability between here and there, basically it is this area. How to calculate the area on here? Divide this area into 2 squares and calculate those 2 squares, right? Then, it's exactly calculating the area. So 55%. This is a more generalized approach to understand probability for continuous random variable, right? So the official name is the probability density function. So this function, this curve, like it doesn't look like a curve, step function. This function is called probability density, and it's if it is high, that means the probability is dense in that area. So this interval has larger probability than another interval with the same length. So that means probability is more dense here, which is represented by higher function. And that function is denoted as lowercase f. Uppercase f was for cumulative distribution function, but now lowercase f is for probability density function, usually abbreviated as PDF. And the purpose of this PDF is to define the probability as an area, right? And of course, it should be always non-negative because probability cannot be negative. PDF is always positive, but what's interesting here is it can go above 1, right? Because it doesn't matter, it becomes like the density can be 3. It is okay because it will be multiplied by 0.1, right? Anyhow, after because the length is the scale of the length is like 0.1, this part can be greater than 1. Anyhow, it will be multiplied by the width. So then in the end, the probability can be smaller than 1. But of course, the total area must be 1 always. Okay. And these are some example PDFs. Uniform distribution is uniform, flat. And exponential distribution has a nicely smooth decreasing probability. And gamma distribution looks like this, also smooth, like a smooth curve. And the normal distribution looks like this. This is what the main topic we are going to study in this chapter. And probability is area. Like as you can see, we are calculating these areas. So probability between 1 and 2 in different distributions. Then you can calculate area here, 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 here. So you see different distributions have different PDFs. So they imply different probability on different on even on the same interval. Okay, the scale is different, and if you learn, like, you must have taken calculus, so integration. I'm not going to use integration again, but I have to say this: it is a key. The connection between statistics and calculus. Why calculus is required? Probability is an area under a curve. That is exactly what integration does. So probability between 1 and 2 can be represented as integration between 1 and 2. Integration from 1 and 2 of function fx dx. And this is another integration, right? So probability density function is used to obtain probability, and obtaining probability is like taking integration of PDF, right? Here, so far it was introduction to continuous random variables. Continuous random variables have uncountably many outcomes, and it has no probability at a point. So because of these two reasons, we cannot use our previous approach, like listing all the possible outcomes. Instead, we have two alternative approaches to define probability. One is based on the CDF, right? This is mathematical way to calculate, to characterize probability. And another way is to use probability density function, which is based on integration. So it can be, both are actually equivalent. So they should imply the same probability, but these are two main building blocks for continuous random variables. Okay, thank you for watching. I will go to the normal distribution in the next video. Bye.